Hello, my lovely students. So now we are looking at dun 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 trig functions. So the Lord of the Rings meme here really is how most people feel when you find out we can do derivatives of trig functions. You mean I thought we were done after pre-cal and now you tell me we're not done? Yes, I am telling you we're not done with trig functions. The good news is though, we're gonna dig into the idea, figure it out, and then I'll give you the cheat sheet. So here's our digging in. Here is our normal graph of sine x. Now, when we look at this graph, I want you to think about just like we were with the velocity and position and acceleration. Remember, the velocity was the slope of the position function. So if we look at this function here, the derivative is the slope of the tangent line. So when I look at this equation, I want to think what's happening at the highs and the lows? What's happening in between those points? So when I look at 0, I'm asking myself, what does the tangent line look like there? It looks like it's increasing. Now, it's kind of hard to tell what the slope of that line is because if you look at my tick marks on the x-axis versus the y-axis, they're not equal. So I moved over 1 unit for pi, but that kind of similar space is somewhere between a half and a unit. It's not a proportional image, so we can't accurately read slope from this graph. So even though the slope looks kind of steep, maybe it's a rise of 2 or 3, it's really hard to say because the measurements here are very weird. But we can say it's positive. Even if I stretch that graph or squish that graph, definitely the slope there is positive. And then when I look at my peak point, I can say for sure at the top of that curve, that is a slope of 0. I can say down here at the bottom of the curve, that is a slope of 0. And I can say in between that top and bottom, that's a negative slope. So we have a slope pattern that is positive, then there's a 0, then it's negative, and then there's a 0. And we know for sure that the zeros are occurring when we look at a sine graph. You can see the 0 points on the graph, the x-intercept points are at 0 and pi. So that peak point is at pi over 2. And then this other peak, the low point rather, the valley, occurs at 3 pi over 2. Our positive slope here is occurring at, these are our inputs, our x values, 0, then pi over 2. Then the negative slope we were marking at pi, then 3 pi over 2. And then if we continued the pattern, just because that's how we always deal with our sine functions, we have the 5 key values there. So if I look at 2 pi, I can see it's doing the same thing as what was happening at 0. I have positive slope again. And I can even see in this graph that it looks like the slope at 0 and the slope at 2 is the same. And it should be the same because trig functions like sine and cosine are periodic with a period length of 2 pi. So every 2 pi, it should be repeating because the pattern on the graph is the same. The highs and the lows are all the same. So this means our derivative function should also be periodic. So it means our trig functions are actually very closely related for derivatives. So let's just leave that there for a moment. Let's look at our next slide. So this one is saying, all right, so we know sine of x. Let's see what happens if we kind of throw that into the derivative formula. Notice I boxed the word if. Can we do this? Yes, technically we can do this. It's ugly. So our limit definition of the derivative, the limit as h goes to 0 of the function evaluated at x plus h minus the function evaluated at x. So that's f of x plus h minus f of x, all divided by h. So if I plugged in h equals 0 now, I would have sine x minus sine x on top, which would cancel out and be 0, divided by the 0 on the bottom. Problematic. So if we were actually going to work this out, the next thing is to use a trig identity that you may or may not remember because it's from the second half of the course. But if we have the sine of a plus b, that is the same as sine a cosine b. Sine stays the same, so it is plus cosine a sine b. So I'm going to make that substitution here. So I still have my limit as h goes to 0. My sine of x plus h, though, I'm going to follow this pattern out. So that is sine x cosine h plus cosine x sine h minus sine of x all over h. So now our sine x's as h goes to 0 is just sine x. Like there's no h in there to get changed. So for the purposes of the limit, those are actually like constants. And then I have my sine h over h. So to actually evaluate this, I would have to do a little bit of rearranging. So, so the limit is h goes to 0, so I'm going to keep these two together. And notice both of those terms I underlined had a sine x in common. So I'm going to factor that sine x out. I will have cosine of h minus 1. This is all over h plus the cosine of x times the sine of h over h. Now all of that still has a limit applied to it. Now it turns out the limit, we didn't do a lot with it, but there is a trig limit for the cosine h minus 1 here. We did do a lot with our trig limit of sine h over h. This guy went to 1. This guy, I believe, goes to 0. And so we end up with the derivative of sine is cosine after a little bit of work. But let's just think about what we were wanting to see from our function. So we need a function that goes up and down between 1 and -1 forever. It repeats every multiple of 2 pi, and it has a value of 1 at x equals 0. So my friend who wrote the notes must have done the derivative as at 0, just a singular derivative instead of the long derivative. The singular derivative would have been a lot easier to work with. But do we know a function that does this? So let me go back to what I wrote on the first slide. So do we know a function that has these x values, but then I'm going to put y values? So if we did the derivative when x equals 0, we would get a slope of 1. We can see it's positive there. If we looked at an actual squared off sine graph, it would look like a perfect diagonal. At pi over 2, it is 0. At pi, it'll be -1. At 3 pi over 2, it is 0. And at 2 pi, it is 1. So look at those y values. And then I'm going to actually plot these points. So when x is 0, y is 1. Then at our next value, we're at 0. Our next value, we're down at -1. Our next value, we're back at 0, and our last value, we're back at 1. So just like our sine graph starts at 0, goes up to 1, comes back to 0, goes down to -1, and comes back to 0. It follows a pattern of 5 numbers, 5 y values like that. Cosine follows this pattern of y values. If I connect the dots with my slightly curved line, I see my cosine graph emerge. So even from looking at the graph, if I think of the slope of the tangent line, the sine graph has a positive slope there. The cosine's value at 0 is +1. Or at pi over 2, the slope of the sine graph at pi over 2 is the top of a peak. It's 0. The cosine value at pi over 2 is 0. So just using our knowledge of the basic sine and cosine graphs, and now our new knowledge of what a derivative is, we can actually figure out that the derivative of sine is cosine. Like we can see it in the graphs. We saw the crazy algebra, and that is our definition. The derivative of sine x is cosine x. Now, if I take it a step further and I look at the slope of cosine, let's go ahead and doodle out our cosine. So I'll just put that right here. So cosine is like that. So that slope there starts at 0, but then at our next one, it's a negative slope, so that's a -1. Then at our next key point, it's back to 0. Our next key point will be +1, and our last key point is back to 0. So for my derivative of cosine, this is my cosine graph. And then this is going to be my derivative of cosine. That graph is 0 at 0. Then at our next key point, it's down at -1. Our next key point, it's back at 0. Our next key point is a +1 slope. And our last key point is back to a 0 slope. Now it's following those same numbers. Like all the same y values we saw for sine and cosine, they're just in a different arrangement. It does start at 0 the way sine does, but instead of going up, it goes down. So it's like sine x, but it has a negative sign. So when we think about our derivatives, one of the things I would write to myself on like my calculus tests when I was still, and my homeworks when I was still getting used to this, is I would write sine x, and then I would write cosine x, and then I would write negative sine x. Now, right now, like just kind of writing them like that, like it kind of makes sense to be like, oh, like that's the way my derivative goes. And so we normally wouldn't bother writing the arrows and being like labeling it as derivative. But let me let you in on like a structural idea in calculus. We're learning all about the derivative and its uses now. But at the end of this course, and then all of Cal 2, you're going to learn about the inverse of the derivative. So the reverse function, the undo function. So when I say, what's the undo for the derivative of cosine? Oh, my undo function will go backwards on this little ladder. So we call that the integral, and it looks kind of like a swoopy S, but this is the direction of integrals. So when you learn your derivatives, you're actually going to want to know them both ways, especially when they're very straightforward like this. Like derivative of sine is cosine. All right, so backwards, antiderivative of cosine is sine. Now we're going to kind of think about here, and I'm going to screenshot our little doodle here. What if I do more than just those initial two derivatives? So if my original function is sine x, then we know the derivative of that is cosine. So that's our first blank here. And then the derivative of cosine must be negative sine. So negative sine of x. Now I'm going to do the derivative of that. So the derivative of negative times sine x, well, the negative is just a -1. It's a constant. So it's just going to carry through on my derivative. So I'm going to have negative, and then I just do the normal derivative of sine is cosine. And now take a look at our notation real quick, because we haven't done a lot of like, oh my God, levels of derivatives yet, but this is where we start it. So first derivative got one little tick mark. It's kind of an angled apostrophe, but it's a straight tick mark as opposed to like a curvy apostrophe. The second derivative was 2 tick marks. The third derivative, 3 tick marks. After that, the tick marks get ridiculous. So instead, we put little parentheses around the number just to be like, this is not an exponent, this is another thing. And now we're saying, when we write it like that with the parentheses, we mean derivative. To me, though, it is also a fair question, if you ever do see that notation, to just straight up ask whoever wrote it down, what do you mean by that? Because it is quite likely in engineering, it'll mean something a little bit different. They might use that notation for something that's more common in engineering, but we've just never had in a math class. So this is how our book chose to do the notation for higher order derivatives. But in future math classes, even in other courses, in other disciplines, the notation might be a little different. Usually, though, we don't have to deal with derivatives like, I don't know if there's really a lot of applications for much past the third derivative. Maybe there is. I'm a math person, so I really don't know. I'm a math education person, so I really, really don't know. All right, so there's our notation for what this parenthesis thing means. Now going back to our trig functions, because we're about to complete a little pattern here. So now the derivative of negative cosine. Well, again, that negative is just a constant out front. So I'm going to write this one here. It's negative. But then my derivative of cosine is negative sine x. Wait. I got negative negative. Haha. So it turns out our fourth derivative here is sine x. Wait. That's the original function. It is. So what if I do the fifth derivative? Yep, it'll be cosine. And then negative sine. And I should be saying of x on all of these. Negative cosine of x. And then again, back to sine of x. So when we are looking at a pattern here, if I wanted to know, like down here, notice the question, what's the 15th derivative? What's the 23rd derivative? Yeah, like we're really ever going to need that. Strangely enough, the thinking about the numbered patterning here and how to like break it down and think about it, that actually does have a little bit of use at the very end of Cal 2 in the section on sequences and series. This weird notational here does show up kind of. So it doesn't hurt to think through this problem. So if we say for n, like if n was 0, then that is our original function, or our fourth derivative, or our eighth derivative. Those were sine of x. If my number is 4 times an integer with 1 left over, like if I plugged in 0, that would be my first derivative, cosine. Or if I plugged in 1, 4 plus 1 is 5, my fifth derivative was cosine. If I plugged in 2, 4 times 2 is 8 plus 1 is 9. My ninth derivative, we can see in the pattern, would be cosine. If my number is 4 times an integer plus 2, which means if I divide it by 4, I have a remainder of 2, which would be a decimal of 0.5. but that derivative would be negative sine x. And then our last one would be negative cosine x. So when we look at these weird numbers, like the 15th derivative of sine x, well, if it was the 16th derivative, that would be divisible by 4, and I'd be back to sine x. So the 15th derivative is 1 before that, and the before that is the bottom of the pattern, negative cosine. But if we're going to focus on the formula, the 4n or 4n plus whatever, we're thinking off to the side. 15 is 4 times what number plus what number? So how many 4s are in 15? So like side thought. 15 divided by 4 is 4 goes in there 3 times, and then it's 3/4 left over, or if we typed it on the calculator, we would get 3.75. So that means 15 is the same as 4 times 3, 12, plus 3 more. So pure coincidence that it was 3 4s and then a leftover of 3. But the leftover of 3 is what we want to focus on. That's a 4n plus 3 number. So that is negative cosine. When I look at my 23, I'll write that one down below. So I know 23, well, that's 20 plus 3, right? Like that's just a normal breakdown, but I know 20 is a multiple of 4. That is 4 times 5 plus 3. So this is another plus 3 remainder. So it is also a negative cosine x. If they asked like the 51st derivative, then, no, sorry, not 51st. Sorry, I'm trying to pick a number that'll be different. Like, let's just go 22nd. No, 30th there. So the 30th derivative, I think about 30, and that's 4. So 4 times 6 is 24, but I could still get another 4. So 4 times 7 is 28, and then 2 more. So the 30th derivative of sine x is that plus 2, which is negative sine x. So again, we're not really going to have a lot of use of it, but seeing the way the number pattern worked here and how we were like decomposing the numbers, that is actually a skill that you can make use of, a kind of pattern matching tool that shows up a little in Cal 2, but also shows up if you go into our proof-based courses for doing our like foo-foo fancy math. So if you're like, that pattern making stuff is kind of cool, like I can get behind that. Also, you use that pattern making stuff in computer programming. Like when you have to write a for loop, like you're using this kind of n notation. When n equals 1, do a thing. And then when n equals 2, do the thing. And then when n equals 3, do the thing. So you say for n equals 1, 2, and then you give it an endpoint. And then it'll run the thing recursively. But you have that notation, and sometimes you'll use that n value inside the loop. So understanding that notation there like has more uses than just pure math. But it is weird. Now, really though, we're just going to use the basic derivative. Derivative of sine is cosine, derivative of cosine is negative sine. So let's read our weird question here that they gave us a unit circle to play around with. If x belongs to this specific interval from 0 to 2 pi only. Okay, so we're not looking way outside our normal numbers, just the 0 to 2 pi normal trig numbers. At which values of x does the tangent to the curve y equals cosine of x have a slope of 1/2. Okay, so let's break this down in pieces. So tangent to the curve and slope. All of that is our key coding calculus words for derivative. So this question is really saying, at what x values is the derivative of cosine equal to 1/2? So I wrote y prime because they called our function y. But I can calculate y prime. If y is cosine of x, then I literally know my derivative. Y prime is negative sine x. So now, well, but the question was, when is that derivative 1/2? Okay, so I'll put 1/2 in place of the y prime. And now I'm solving a trig equation. So this is another pre-cal skill that you're like, oh, I can leave this behind me. Nope, here it comes back again. Now, the good news is, though, they told us we're only looking from 0 to 2 pi. And 1/2 is a unit circle value. So this one's actually going to be more straightforward. And this is why, like, in Cal 1 and Cal 2, we tend to keep the values on the unit circle. In the real world, though, when you ask this question, like, you still do this process, but it's not going to be 1/2. It'll be like 0.374. And you're like, why is it that? Because that's what my machine measured it to be, so that's what I got to solve for. But for 1/2, we'll get to use our unit circle. Now that 1/2, though, is making things weird. So I am going to divide both sides of my equation here by -1. So I really have -1/2 equals sine of x. So I'm asking here, when does the sine function have a value of -1/2? So we got to remember on our unit circle, the ordered pairs are cosine first. Hold on. Cosine of the angle and then sine of the angle. I am deliberately using theta here, so I am not using x and y. So even though the first coordinate, we call it an x value, for the unit circle, don't think of that as the input versus the output. The unit circle is actually a non-functional tool. The input on the unit circle is the angle. The output of the unit circle is both of those values, the cosine value and the sine value. One input, two outputs violates the definition of a function, but it is a very useful math tool once you understand that dual nature. So we're looking for, where are the y values -1/2? So not in our first two quadrants, which makes sense because that's where the y-axis is positive. So, there we go. And then over here. Now they did say in the interval from 0 to 2 pi. So that is our ninja hint that we want to answer in radians. So we are going to pick 7 pi over 6 and 11 pi over 6 as our two solutions that answer our question. At what values of x does the curve y equals cosine of x have a slope of 1/2? The slope is positive 1/2 on cosine when the input is 7 pi over 6 and 11 pi over 6. And now my brain is just like, yeah, it starts out, it's negative for the first half of cosine, and then it's positive for the second halves. So as weird as it sounds, that does actually track. Like, let me try to draw a decent cosine graph. Not the best, but a positive 1/2 slope is kind of like that. and like that. It's not a 45-degree line. It's more laid down. It's actually a 30-degree line. No, it's not. I take that back. Cosine value is not slope. I did that wrong. I lied. But those are roughly those two values. 7 pi over 6 is close to pi at the bottom. 11 pi over 6 is close to 2 pi at the top. Now, to keep using our lovely skills that we just barely learned, our product rule and our quotient rule, don't hate the messenger. We're going to work with this guy. Now, you've got these in your homework. These are gnarly to work with. They are ugly. But the more you practice using these rules, the more comfortable and familiar you get with them, the faster you get at them, the more easily you can pull them up and use them. These are tools that you want to get familiar with. Your job on a math test is to show me that you are proficient with the tools that I'm showing you how to use. So you are going to see something that makes you use the product rule on this next test. You will see something that makes you use the quotient rule on this next test. And inside those, there are probably going to be some weird functions as well as just normal polynomials. So this is ugly, but actually annoying, but fair test question. This is actually going to use the product and the quotient rule inside it. So I have overall, it's a big fraction. So overall, my rule is the quotient rule first and foremost. So let's focus on the structure of the quotient rule. Let's remember that structure. So when I am doing the derivative of, like I wrote it before as high and low, and then I said it was low d high minus high d low, square the denominator, or some people will say it's over low squared, and away we go. So our quotient rule starts with our low function times the derivative of the high function. So right now, I'm just going to write in the pieces with the d's that say do the derivative. So this is s, this is low, this is high. So our derivative of s with respect to t, that's what ds dt is. That is just a shorthand for s prime, s prime. So low first, we're going to have t squared minus 1, and then d high. So I'm going to make my d orange just for a little color coding. And then I'm going to make my high, I'm going to relabel it pink. So derivative of high, t times sine of t. So low d high minus, now our high, the original high, t sine t, d low, our low is that t squared minus 1, all over low, or square the denominator. So t squared minus 1, whole thing squared. Now, I have used my format for my quotient rule, but I still have d's in there, so I need to do more calculus work. Your job on the test is to show me you can do calculus, not necessarily that you can do all the algebra that would follow if we needed to do more. We don't here. All we want is an expression that has no calculus for the derivative. So I'm going to evaluate now my derivatives for each of those pieces. Now over here, my derivative of t squared minus 1, well, that's a polynomial. I know that guy. That'll be bring down the power 2t to the first minus the derivative of a constant is 0. All right, now I'm going to rewrite my other piece, the t sine t. And up front, I got my t squared minus 1. Now there's a minus in between. Don't forget that minus sign. It is very easy to lose it in your work, especially if you have stray pencil marks. So I like to be very deliberate. If I'm afraid I'm going to lose a symbol, I'll like go over it several times. So it is like very obvious on my paper. This is here. Don't forget it. And that's just because I'm very ADD. So now we got to figure out the derivative of t times sine of t. So that's our sidebar here. So this is a product rule. This is an A times a B. So let's make another side note. The derivative of a product is keep one times the derivative of the other. So we're going to keep A times, let me use my D's, dB, plus, then I keep B times dA. So some people will say like AB prime plus BA prime. Some people will say AB prime plus A prime B, like whichever way you want to write it so that the form of it makes sense to you. But the whole idea is one of them has a derivative, the other does not. And then I could rearrange it. I could write BA prime first plus AB prime. Like I can, BDA first and then ADB second. That's fine. So our A here is t. So when I do my derivative here, I'm going to have t times the derivative of sine t. Then my product rule had the structure plus. Now I'm going to keep sine t, and I should use parentheses, careful substitution, times the derivative of my first thing, which was t. So first thing times derivative of the second plus second thing times derivative of the first. Now I'm going to do my derivatives inside that. So I keep my t. The derivative of sine t is cosine t plus I still have sine t. And then the derivative of t is 1 t to the 0, which is just 1. So our derivative of this weird product is t cosine t plus sine t. So rewind it over here. T cosine t plus sine t. Done. Do not do anything else. The calculus step is done. I did my weird internal product rule derivative that was required. No more derivatives internally needed. That is ds dt. Could I clean it up more? Yes. Do I have any reason to do so? No. If this problem wanted me to do something else, that's when you can throw something at me, preferably something light because I'm not a horrible mean person. So usually when you do a nasty derivative like this, we're not making you do anything else with it. If you did have to do a problem like in some other discipline where the derivative was nasty, you'd be using a computer. But you do still need to understand the structure of derivatives, how the quotient rule works, how the product rule works. And that mostly you need to understand that it's not simply the derivative of each piece being multiplied or the derivative of each piece on the top and the bottom being divided. That multiplication and division make derivatives weird. So we also have The other guys. Uh-huh. Now, the fun little fun being a relative term, I know. But challenge problem on the side. Can you prove the derivative of tangent is secant squared? Yes, you can. You will need, here's your recipe, the ingredients. You need to know the quotient rule. You need to know that tangent is sine x divided by cosine of x. You need to remember that sine squared of x plus cosine squared of x equals 1. And you need to remember the fact that 1 divided by cosine is secant. So I want you to think, like, if tangent is sine over cosine, oh, well, the derivative of sine over cosine, that's a quotient rule. Which, like, oh, why'd you do that, Dr. Liz? I know. But what does our quotient rule end with? Low d high minus high d low. Square the denominator. Our denominator is cosine. So we'll have a cosine squared on the bottom. But what is 1 over cosine squared? Oh, that's secant. 1 over cosine is secant, so that'd be secant squared. Now look over at our derivative for tangent. Boom, secant squared. Because tangent has a cosine on the bottom, and quotient rules always end up with the denominator squared. So, similarly, cotangent follows a very similar pattern, but it's got to be a little bit extra. And here's what you're going to see a lot in calculus. Like, remember before, derivative of sine was just cosine, like, all right, sine, I like you. Cosine had to be a little extra. Like, no, I can't just be sine. I have to be negative sine. Like, just had to be more. All right, I see you, C function, because it starts with a C. And then check out our other C functions here. Look at that. Cotangent, similar kind of pattern, but it's got a negative. Cosecant, similar kind of pattern, but it's got a negative. So all of our trig functions, if they have a C, the derivative has a negative. And then it's going to turn out way later, the antiderivatives have negatives, typically. All right, so our derivative of cotangent, cotangent is cosine over sine. So we're expecting to see a sine squared. 1 over sine is cosecant. So we do see the cosecant squared, but there's a negative because on top you'll end up with negative sine squared plus or minus cosine squared. Like instead of getting a positive one on top, you get a negative one on top. But you can prove it. The proof is almost identical to what we did for tangent. Like, not that we did it, but if you did do it, it's very similar. Now, secant is a quotient. That's the derivative of 1 over cosine. So the top thing is a constant. So when you do the derivative of the top, you get a 0. So it actually makes the working it out a little nicer, but you'll end up with this weird convoluted like trig question, trig identity proof. So you end up having to prove that when you finish the whole formula, it's secant tangent by doing trig identity stuff. And then similarly, so like derivative of tangent is secant squared. Derivative of secant is secant tangent. So the tangent and secant are like very closely related. And they're very similar to our sine. None of those guys are negatives. They're all positives. Tangent gets the secant squared because our quotient rule gives us a squared. Secant, though, is weirder because one of the parts on top goes to 0. We're not going to get a nice thing turning into a 1 on top. We're still going to have stuff left over on top. So tangent is sine over cosine. Secant is 1 over cosine. So the derivative of secant is sine over cosine squared. We still got that cosine squared pattern, but the top only had a single thing. So that's why we end up with this weird compound derivative. So it's extra work, but it can actually be useful to work through the derivatives of all 4 of these the long way. It's good practice with your quotient rule and good practice with your trig function derivatives. So as tedious as it sounds to do, it's actually worth it to do because it'll make these definitions stick. Yeah, that is not what I wanted, computer. I wanted to scroll. All right. So now we're going to kick it up a notch. I've got the thing -3 minus 2 secant x times sine x. So I could distribute here, but then I'm still going to have a product rule. So I'm just going to go with the derivative in the format it's presented to me rather than try to distribute the sign, because it's going to be about the same amount of work. In fact, it'll be a little less if we don't do the distribution, because then we're not taking an extra math step. So this is still overall structure-wise, though. This is an A times a B. So derivative of A times B is A B prime plus B A prime. Now, it's real tempting to not write that formula down. Write it down. Every time you are doing one of these problems, write it down. Because every time you write it down, it sticks in your head more. Write it down the same way. Pick whichever way you like to write it, but then write it that way every time you're doing it on a problem. So that way on the test, you don't have to remember this, because I'm not going to tell you the product rule formula on the test. Now, if we give you a weird trig function, we might give you this part off to the side. Like, I haven't seen the test. We haven't written it yet because it's after spring break and I got more shit to do. But product rule, quotient rule, you will have to know those for the test. So every problem that makes you do it, write the form down. Get used to the form so that way it gets ingrained in your head. Now, once you're real comfortable with it, you don't have to write it down no more. So if you took Cal 1 already in the past and you've done this homework, and you're already at that phase, all right, cool. I'm not going to take off points if you don't do it. But if you're learning this for the first time, that is a really good way to get information to stick, is to write it down several times and then use it immediately. So we wrote it down. Now I see my A, and that's what I start with. So -3 minus 2 secant x times my derivative of B. So B is sine x. So derivative of B, derivative of sine x is cosine x. So this is B prime. This is A. And then we have a plus in between. So I make my extra plus. Now we're going to do B, which is just sine x. And now we're going to do A prime. So A prime is going to be a little bit extra. So I have -3. That is just a constant, because then it's minus something else. So anytime I have a sum or difference, addition or subtraction of several things, I can do each one of those things on its own. So -3 on its own is a constant. The derivative of a constant is 0. Minus 2. So that is a number being multiplied to the function. So that's a constant multiplication. That carries through for our derivative. So I have the 0 from the derivative of -3. Now I keep the -2 times. Now I'm going to do my derivative of secant, which is our formula that they rewrote for us up here. That's secant x, tangent x. And that's our A prime. Now, here, again, you can clean it up if you want to, like if that kind of gives you a thrill, especially if you notice like the secant and the cosine over here are going to like cancel each other out. Like, you want to do that, go for it. And I kind of want to do it, so I'm going to run through it real quick. So we'll have -3 cosine x, and then secant x times cosine x is 1, so it's just -2, plus, now sine x times 0 would be 0, so I'm not going to write that, but I'll have, well, it'll be plus 0, so I'll write the 0 as a placeholder, and then -2 times sine x times secant x times tangent x. Now the secant x is 1 over cosine, and then sine over cosine is tangent. So we have tangent times tangent, so this is -2 tangent squared x. So we have negative 3 cosine x minus 2 minus 2 tangent squared x. If they wanted us to do a second derivative, it is easier to work from this bottom formula than it is from the original format. But if all they asked for was the first derivative, done. You don't have to clean it up. I only did it because I'm a math geek and I'm also teaching a lot of pre-cal and I just wanted to see it clean up. Whoa, thank you for computer for going weird. All right. One more. Now this one had to be extra, asked for a second derivative. And the function we're starting with is cosecant of x. So the first part of this we can accomplish just by like scrolling back up and looking, but we just looked at it and I happen to remember it because my teachers were mean. I had to remember frickin' everything. So y is cosecant x. Y prime is negative cosecant x cotangent x. Our tangent and our cotangent are just one single function squared. Our secant and our cosecant are the two functions. This is a c function, so it has a negative sign. So that is like the pattern recognition going on in my head to do this derivative. But now it's a product of two of the ugly trig functions. So we're still going to do our product rule. I'm going to write it with the d's. So the derivative of a times b, I'll do a little color coding this time. This is a db plus b dA. Now, this has a negative in front of it. Two ways to go about it. I can include that negative as my definition of A or my definition of B, or I could just write it in front of my derivative with like big parentheses. Since it's just a negative sign, I'm just going to incorporate it in. But, feel free if you don't, if it's like a weirder number, you don't have to do it that way. So for this is what I'm calling A. This is what I'm calling B. So A is negative cosecant. So when I start doing my second derivative here, so I write y with 2 tick marks. I start with A. So negative cosecant x times the derivative of cotangent x plus, now I write my cotangent x times the derivative of negative cosecant x. So hopefully the colors are like helping you guys focus on what's the structure from the product rule versus what's each of the pieces that were the product pieces being multiplied. Now we're just going to do the derivative parts. So just recopying my label, I keep my negative cosecant. The derivative of cotangent and tangent are going to have those square functions with it. In this case, and it's a c function, so it's going to be a negative. Cotangent goes with cosecant. So this is cosecant squared x. Negative cosecant squared x is the derivative of cotangent. That was just me kind of walking y'all through why I remember that. All right, now we still have the cotangent of x. And then we have a negative sign times the derivative of cosecant. The derivative of cosecant is what we had before, negative cosecant cotangent. So I do technically have here like -1 times the negative. So there is a negative negative that would get canceled out there. So you could like cancel that as you're typing in the result, but we could just leave it like this. And if you type it in like this, WebWork will accept it. Like a lot of these questions now, as long as you type it in exactly what you wrote, it'll take it. Because there's too many other ways you could write this answer. So in order to determine equivalency, WebWork is taking numbers and plugging it into the x value, a bunch of different x's, and then it takes those same x's and plugs them into your answer. And then it compares the values. Did my x values for my programmed in correct answer, when I got the y values, did it match the y values that your typed in answer gave me? If the y values match for all the random x values it picks, then it says your answer is correct. This is why, though, like rounding to a certain number of places can shoot you in the foot in WebWork when we're doing functions. So like later on, when we start evaluating the trig functions, you got to write square root of 3 over 2. You can't put 0.866. It won't take the 0.866 even if you wrote 9 numbers because it's not the same as the square root of 3 over 2. All right, so there is our crash course insanity in trig derivatives while still using our product rule and our quotient rule. So good practice in here. So when you guys are working this homework over the weekend, write out the product rule, write out the quotient rule, because you are going to need that over and over again. But it's also a good idea now to start writing what I call a cheat sheet, or a formula sheet would be a more politically correct term. Start writing down these extra formulas we get. So let me scroll back to it. So these guys, write down these on your formula sheet because these are the kind of things we'll give you to reference. We're not going to expect you to remember this out of thin air necessarily. Sine and cosine, though, you're going to use those derivatives a lot, so those you should memorize. So you can have like 2 cheat sheets. One is the like, I'll probably get it written out, and the other is I need to memorize this. So on the I need to memorize it, every time a problem uses it, write it down until it's stuck in your head. And it sounds silly, but say it out loud while you write it, because the hearing yourself say it helps it stick. All right. And see, there it even says create your own formula sheet, see? So this was a shorter lesson. I know, even though I recorded it and it's still kind of a long video. You can always go to the Math Gym for help. Flawn 3.02.08, or for future semesters, hopefully it'll move and we'll have a bigger room. But far as I know, spring 2026, it's still in the Flawn building next to my giant office of 12. All right. I will see you guys next week.